Now we begin Chapter 6, and in Chapter 6, we are beginning the thermodynamics portion of this course. This is very introductory thermodynamics, and next semester you're going to learn the principles behind these relationships that we will be using. The key here is that we are beginning to get more and more information to solve our material balance problems. And equilibrium relationships, which is what thermodynamics is, provide some of those connections that we can use for our calculations. So we are going to review here some basic principles, the pressure temperature diagram, pressure volume diagram, and you will be reintroduced to vapor pressure, as I know that you've learned that already in your lower division chemistry course. And then we are going to, the two equilibrium relationships that we are going to use are these ideal situations. We will use Rayleigh's law and Henry's law. And in this course, we will only consider one condensable component. So we will not be doing, I believe it's section 6.2 that is on multi-component equilibrium calculations. We're saving that for thermodynamics. So we're going to learn how to calculate the vapor pressure of a liquid, and we will learn how to perform material balance on a two-phase system with one condensable component. And later in this chapter, we will also learn about liquid-liquid and solid-liquid systems. So there's a lot of different processes in chemical engineering that have two phases. In this particular lecture, we are focusing on a gas phase and a liquid phase, and we assume they're in equilibrium, otherwise we cannot do any calculations. So this happens in reactors, okay? There's gas and vapor reactors. This is an important separation concept, and we also do evaporation. A flash drum is really just a single stage of a distillation. And absorption is gas scrubbing. So that's another gas-liquid process. So we are going to revisit over and over the material balance principles that you've learned already, but now we are going to combine them with the equilibrium expressions in order to complete process material balances. So keep in mind that equilibrium expressions relate composition in two phases in equilibrium. Okay, so if we know something about the composition in one of the two phases, then using an equilibrium expression, we can know the composition in the second phase. So if we have a pure substance, okay, we can look here at this pressure volume diagram. And in this diagram, we have the vapor here. These are isotherms. The red and purple lines are isotherms. So those are, they're all at the same temperature, but the pressure and the volume changes. And that's the behavior of the gas, is that how you see the isotherm. If you're above the critical temperature, then you have a continuous continuous model to represent the behavior. But below the critical temperature, which is the red line, you have a discontinuous relationship. So it meets at where you have this mixture of vapor and liquid until you have all vapor, and then again you have a continuous relationship. So this line here is called the phase envelope, which envelope. Okay. So underneath that phase envelope, we have two phases of vapor and liquid. Okay, so this is all in here, vapor and liquid. Here we have liquid, and then we have solid. Okay, so we also have a type of phase envelope where we have liquid. So then, but the phase envelope that we really refer to as this heat hump here, and under there we have a mixture of gas and liquid in equilibrium. Okay, so I'm focusing on these different aspects here. This again, we're under the phase envelope with the orange hashing, and we have saturated vapor and saturated liquid. What does that mean, saturated? That means the vapor has as much liquid in it as it can, and the liquid has as much vapor in it as it can. That's what saturated means. And then we have the vapor section. Okay, so, and this is called superheated vapor. So if we're above this curve here, then it's superheated. All right, and now what we're going to learn here is that there's that we can, if we know the temperature of our system, okay, then we can calculate the vapor pressure of the liquid phase. So we can design that this is going to be an empirical relationship. Pretty much everything in thermodynamics is empirical. So the systems are complex. It's difficult to create first principles models, although they have developed them. They're extremely computationally intensive. So it's easier whenever you can have an empirical relationship and look up important parameters off of a table, then you have an easy calculation. Okay, so it's empirical means the relationships are based on the observed behavior of fluids. So the relationship between vapor pressure and temperature of fluids is developed from observation. And what was observed? It was observed that the plot of the log of the vapor pressure versus the saturation temperature is approximately a straight line. And that information was used to create Antoine equation. So you need to know this very well, okay? And now in our book, it's a base 10 log, and it doesn't matter. The key here with all of our tables that we use is that you need to pay attention to the units that table specifies. So in the table in the Felder book, we have the base 10 log of P, and the pressure is going to come out in millimeters of mercury. Okay, so let's use, I will do a quick calculation here. Okay, calculate the vapor pressure of ethanol at 60 degrees using the Antoine equation. Okay, so we look up in the back of the book, and we have A, B, and C, and this is our formula from the table in the back of the book. If you look at that table B.4, okay, if you look at that table, then you'll see this equation is given there for you. Okay, so you just have to plug in the A, B, and C. And here you know your temperature, and then you can calculate your PSAT. Okay, so it's a base 10, so we take 10 and raise it to the power of all of this. Okay, so now if we plug in the A, B, and C, we get that PSAT is 351.7 millimeters of mercury, and we can also convert that to 46.9 kilopascals. So let's do a comparison. If we do the calculation for water, okay, I did the calculation when you weren't looking, and we find that PSAT of water at the same temperature is 20 kilopascals. So the question here is which of the two is more volatile? ethanol or water? Well, the one that has the higher vapor pressure is more volatile. So we can see that ethanol, and you know this from your own personal experience, that ethanol is more volatile than water. Okay, so now let's move on to the Rails law for one condensable component. This is our first equilibrium relationship. Okay, this is Rails law. Yi times the system pressure is equal to the mole fraction in the liquid. Okay, so Yi is in the vapor, Xi is in the liquid. P is the system pressure, total pressure, and this is the vapor pressure of the water. Okay, so now if we have this system, we have water in the liquid phase, and we have air and water in the vapor phase. So what is I, first of all, here? I is going to be, it has to be, in other words, which species are we talking about here? The only species present in both phases in appreciable amounts. I mean, there's some water in or some air in the water, but we're going to use a different relationship for that because it's very, very dilute. So it's effectively negligible. Fortunately, it's not negligible to the fish because that's how they breathe. But it's, so the I that we're referring to is water. Okay, I is water, and Xi is 1 because the only species in the liquid phase is water. So that means that we have, if Xi is 1, then we can just remove it. It's still there, but it's 1, so we can just kind of ignore it. And this is our simplified relationship for Rails law. Now, it's simple, but you'll see that the problems do become quite cumbersome. Okay, because we have to calculate the PSAT, and then we have to find the mole fraction, and so this is our first equilibrium expression. So if the gas is not saturated, we write HR, the relative humidity, is equal to the mole fraction times the total pressure divided by the vapor pressure. And YIP, as we know, is the partial pressure. Okay, so let's do a calculation. We've seen this one before, but I'm adding a little Rails law twist to it. That we are going to combust methane with 30% excess air. Air is fed at 100 degrees C in 10 bar with 50% relative humidity. And the products leave the furnace at 30 degrees C in 1 bar. Okay, so we need to know if the products leave, okay, is there liquid water present? We can answer that question using Rails law. Okay, and our material balance. So now let's think about this problem. Okay, this is a boiler furnace. All this water is in the gas phase in this high temperature in the boiler. And we're going to cool it down. And as it cools down, we begin to condense liquid, presuming that we cool this below the saturation temperature of the water in this vapor. Okay? So let's see how we do this calculation. First thing we want to do is we're going to use the Antoine equation for water vapor pressure. Okay, we do that calculation. It turns out that at 100 degrees C, the P start, the inlet, is 101.2 now. Now we apply Rails law, and we would have the mole fraction times 1,000 kilopascals, which is 10 bar, is equal to 101.32. However, this Rails law only applies to equilibrium. So since we specified that we have 50% relative humidity, then let's plug in let's use our relative humidity equation. So we have, we know the P, we know the PSAT, okay, 101.29, and we know this. So now we'll find our mole fraction, okay, and it turns out that our mole fraction is 0.05. So our inlet stream has 5 mole% water. Okay, so now we are going to do the calculation on the exit stream. And this is a little more complex, but watch what we do here. Okay, so we have 5 mole percent of water entering. Okay, then we know that the moles of nitrogen plus oxygen here, it adds up to 12.38, has a mole fraction of dry gas is equal to 0.95. Okay, and so we can use that mole fraction of dry gas and divide that, our 12.38, by the mole fraction, its mole fraction, which is 0.95, and we find that we have 13.3 moles of humid air entering, and we can take the difference between 13.03 and 12.38, and that's going to give us how many moles of water we have entering. Okay, so now if we look at the exit stream, if we do our material balance, okay, the exit stream now is at 30 degrees C, and our P star in the outlet is 4.24 kilopascals. Okay, so we can again calculate. In this case, we assume that it is saturated, and it's saturated because we've cooled it down, 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 and so the water remains in the air. It's saturated and there's liquid water present. So that gives us the evidence that that stream is saturated. So then the Y of H2O is 0.042. Now let's do a material balance and find out how many moles of water we have go down. We have 4.2% in the stream is water. Then the dry gas, which is 11.38 moles, is 95.8% of the total stream. Okay, this is the moles of dry gas out. Okay, the nitrogen, the oxygen, and the CO2. Okay, so this is our exit stream here, and we have now we have a total moles out of 11.89 moles of humid gas out. All right, and so we have a total of 11.89 moles of humid gas, and we have 11.38 moles of dry gas. So that means we have 0.51 moles of water in the vapor. Okay, so this is the water coming out in the vapor stream. We did the exact same calculation on the inlet stream to find out how many moles of water we had in the inlet stream. Now we do the same calculation on the exit stream and see that we have 0.51 moles of water in the vapor stream. We have less here. No, even though it's saturated, it's much cooler. So 0.51 is fewer even than we had entering in the vapor stream, which tells us we know there's going to be water in the liquid. And don't forget that in our reaction product, we produced 2 moles of reaction product of water, 2 moles of water in the reaction product. Okay, which means that the total moles we have in our system is the amount that went in the vapor plus the amount that we produced in the chemical reaction, or the total moles in the process, leaving the process, is 2.65 moles. So how much of that is in the liquid? We take 2.65, we subtract the amount in the vapor, and then we are left with 2.14 moles of liquid water leaving the system. Okay, now you try a calculation. This is video quiz 6.1.1. Methane is burned to complete combustion with 30% excess dry air. I'm sorry, 30% excess air. Yeah, it's not dry. The air enters at 25 degrees C in 1 atmosphere at 50% relative humidity. So first, calculate the oxygen per mole of methane entering the process. Calculate the flow of nitrogen per mole of methane entering the process. And calculate the flow of water per mole of methane entering the process.